You can see my screen?
Yes.
All right, so graphing rational functions. Okay, I'm just going to create a random one here, and then I'll tell you about all the different parts that make up this rational function. So let's say I had x minus 1, x plus 2, x minus 1, x minus 4. Okay, so this is a rational function. We call it a rational function because there is a variable in the numerator and there's a variable in the denominator. Okay. Now, there are a couple of features about this graph, and I want to kind of go down the list, and maybe I'll go through another example and see if you can let me know if you're if something doesn't make sense. Okay. So the first thing that we have is we have something called the X Intercept. So X Intercept is where the graph crosses the x-axis. So, well, first up, do you see how do you see a matching pair in this rational function?
X minus 1.
Yeah. What we're going to do is we're going to cross off just this x minus 1 here.
Both
and that's
of them?
going to, yeah, both of them. They're going to cancel each other out, but we're not going to completely get rid of them. They're still going to be needed for later on, but at least this is something unique about the graph here. Okay. So x-intercept, if you see any numerator that does not cancel out, that's where your x-intercept is. So the x plus 2 is in the numerator. It doesn't go away. There's no matching pair to. And then what we do is to find the x-intercept, you just set the parentheses equal to 0 and solve for x. So if I solve for x, x equals what?
0.
Well, if I get x by itself, I need to move that 2, right? So x equals...
Oh, 2.
What happens if I move the 2 to the other side?
You got to subtract it.
Yeah. So x equals what?
It equals 2, right?
Well, not quite. The 2 and negative 2 goes away. So what's 0 minus 2?
Negative 2.
Mm-hmm. So x equals negative 2. So anytime you want to solve for an equation like this, you're basically just going to flip it to the other side and you change the sign. Okay, makes sense?
Mm-hmm.
Right. So that's one property that we have to involve, and we'll come back to that. The next property we have to involve is something called the vertical asymptote. So the vertical asymptote is going to be the denominator expression that does not cancel out. Okay, so what's the denominator expression that does not cancel out?
Negative 4.
Yeah, and then we're going to do the same thing here. We're going to set this expression equal to 0.
Okay.
And what's x equal to?
4. Positive 4.
Yeah. Now, vertical asymptote is where the graph doesn't exist. Okay, so X intercept is where the graph crosses the x-axis. Vertical asymptote is something else. It's where the graph doesn't exist. Okay, and then we have two more categories. Next one is we're going to deal with this x minus 1. Okay, this cancels out, but there's something special about this, and we call this a hole in the graph. So the hole is going to be factors that match and cancel out. Or that comes from factors that match and cancel out. So you see that x minus 1 there? We're just going to pick one of them and set it equal to 0.
You want me to tell you?
Mm-hmm.
It's 1.
X equals 1. So there's a hole at 1. Okay. And finally, we have something called the horizontal asymptote. The way we find horizontal asymptote is we're going to count the number of x's in the numerator and count the number of x's in the denominator. How many x's are there in the numerator?
2.
2. How many in the denominator?
2.
So if the numerator and denominator are the same, then the horizontal asymptote is just going to be the number in front divided by each other. So there's a hidden 1 here, so 1 over 1 is 1. And it always is going to be a y equals.
Okay.
So there's going to be a couple things coming together as we go to Desmos. We're going to have a point. We're going to be able to locate where the point crosses the x-axis. We're going to be able to figure out where the graph has a vertical asymptote. We're going to figure out that there's a hole at 1. And then there's also a horizontal asymptote at y equals 1. So I'm going to visually show you what these all look like on the graph. Okay, so let's go to Desmos and we're going to type this whole thing in. We're going to type the original function in. I'm not going to pretend like as if I erased the cross out sign. I'm going to just type this all in. Okay. Let me go to Desmos. All right, let me share the screen. All right, so here we're at Desmos. Go to Graphing Calculator. Now I'm going to type this function in. So parentheses x minus 1, x plus 2 divided by, and it's going to give you that nice division sign there, x minus 1, x. Okay. We can zoom out a little bit here. Okay, but we have some properties of this graph here. So we're going to sketch this graph out. The way we can do that is if you go to see that table, convert to table there. You hit that that gear circle, and then you hit this here. And we're gonna get some order pairs. Okay, the order pairs doesn't have to be exact, but we just want to pick some points around 0. And it's nice having all those dots show up so we can kind of know how the graph's going to look. So I'm going to take these order pairs. I'm going to plot the graph. And I want to show you.
Are you supposed to skip 4?
Oh, yes. There's something special about 4. Okay, you know what? Let's do that. Let's hit 4. We're going to see what happens here. Okay, undefined. And then one's a whole, one's a vertical asymptote. So we're going to see that happen. You know what? Let me go back, because I'm going to go back and I want to create an outline for us, and then we can kind of work around that outline. It's a lot easier to graph if the outline is in front of us. Yeah. So let me go back to my other screen. Okay, so we're going to create a coordinate plane. And what we're going to do is we're going to draw our dotted lines. So there's a dotted line, vertical asymptote at x equals 4. So that means we're going to go to 4 and we're going to draw a vertical line all the way up and down 4. The nice thing about asymptotes is that it kind of helps us know where our boundary is. If we know where our boundary is, it's a lot easier to kind of build the graph around the boundaries. So vertical asymptote is a dotted line. Okay, does that make sense?
Yes.
Okay, there's a horizontal asymptote at y equals 1. So we're going to be doing a horizontal dotted line at y equals 1. So you're going to go to 1. And you're going to draw a dotted line. There is a X intercept at -2. So at -2, that just means it's going to be a point that lives on the x-axis. So we're going to highlight that point because we know the graph's going to go through that point. And then y equals, and then there's a hole at 1, but, oh, it's undefined, right? It says undefined. Okay. So what we're going to do is, to help us with it, we're going to go back to Desmos. And if I hover right around 1, it's kind of showing up as...
I can't see your screen.
Okay. Okay, so if I hover right around 1, it looks like the graph is at 1, -1, right? There's a hole there because you see how it's undefined. But I know it looks like it's going right through that point, but it's a hole. So when we go back to our graph at 1, -1, we're just going to put a big hole there. All right, now all these order pairs, I'm just going to put them onto my paper and I'm going to graph it. So just some points around, just so enough for me to kind of know some of these anchor points here. Doesn't have to be completely accurate, but we just want to be able to have an idea how, you know, where these points are going to go.
Are you writing on the paper again?
Yeah, that's what I'm doing right now.
I can't see it.
Yeah, I can't share 2 screens at once, but I will.
Okay.
But I'm just copying this table onto my paper. Okay, -2, 0, -1, -1.2, -0.2. And you see how there's a hole there. So I'm just going to get that graph, just go through that hole. Now, the nice thing about these dotted line is that it kind of helps us guide where the graph's going to go. So I know my graph's going to get closer towards these dotted line without ever reaching it. So they're going to kind of act like magnets. They're going to kind of draw the graph closer towards them. And over here, 5, 7. 6, 4. 7, 3. Okay, so we kind of have an idea. The graph's going to kind of have a curve shape, and it's going to end up, as it gets further and further away, it's going to end up hugging these lines here a little bit. All right. How does that? Any questions so far?
No.
Okay. So you can kind of use this as my model to build functions with all these different features. Okay. You want to do one more here? I can walk you through the steps. I'll create one, and then you can see how much you can do. How's that?
I'll try.
Okay. Oh, and then one thing I didn't bring up is you saw how for horizontal asymptotes we counted the x's, and there were 2 x's here and there were 2 x's down here.
Mm-hmm.
If there were more x's below, let's say there's x squared here, then all of a sudden there's more x's below than above. So if there's more x's below than above, then your horizontal asymptote will always be 0.
Okay.
So if you're only going to have 2 scenarios, either they're the same. If they're the same, just look at the number in front. If there's no number, then it's just 1. If the bottom has more, then it's always 0. It's always y equals 0, which is just going to be this line.
Okay.
Okay, let's try this one. Oh, I forget. One more thing we have to do. It says to put in standard form. So standard form means we got to FOIL all this out. So let me show you what that looks like. If I were to take my function, and if I were to FOIL this out, so I'm going to distribute the x through, then distribute the -1 through. So this is x squared plus 2x minus 1x minus 2. And if I FOIL the denominator out, I get x squared minus 1x minus 4x plus 4. I'm just distributing this through, multiplying all the different parts. And now I'm just going to combine like terms. The middle terms will always add, combine. So 2x minus 1x, this is 1x. And then here, combine middle terms. So that's standard form. So after you create your factored form, you're going to have to FOIL it out and get it down to a standard form like that. Okay, let's try this one here. Mm.
It's only supposed to be one on top.
Yeah, yeah.
Okay.
Let me put a 1 up there. Let me know if you want to look at a reference sheet or.
So, I do my numerator first. X plus 2 equals 0. And I subtract 2 on both sides, and that leaves me -2.
Right, but what category does that fall under? Is it an X intercept? Is it a hole? Is it a horizontal asymptote? Is it vertical asymptote?
The X intercept.
So X intercept is the numerator expression that does not cancel out.
So this one has to cancel out.
Yeah, you see how this one, there's a matching pair here?
Mm-hmm.
So that's telling
okay,
us
okay.
it's something else, right? Something else.
What about the X that's on the outside?
Yeah, that's it. This is how we get to our X intercept. So what do we do with this?
We put X over X minus 5.
Well, what do we do here? We just took that expression and we set it equal to 0. So same thing here. What can we do?
Make it equal to 0.
Yeah, just make that X equal to 0.
So would it be X plus 1?
No, just X equals 0. Well, there's a 1X here, but that 1X, if we divide it out, it goes away. It's not 1 plus X, right? If it was 1 plus X, then we'll have to move it, but that 1 will just disappear.
Okay.
It's like dividing by 1. So 0 divided by 1 is still 0, so it's like as if nothing changed.
Okay. And then we do the vertical asymptote, which is X minus 5 equals 0. And we add 5 to both sides. Give us positive 5.
Mm-hmm.
And then the whole is 1? Or would it be 0?
Yeah. How do we find the whole?
If it's in front of the X intercept.
How do we find the whole here?
We factored out.
Mm-hmm. Or what do we look at? How do we know what to look at to find the whole?
We look at what's in front of the equation, the numerator equation, and the
Actually,
denominator.
we look to see what has an X across it. So whatever cancels out is where the hole is located.
Oh, okay. So would it be 2?
Well, this is where we look. So where's the hole?
Would it be -2?
So we're going to go to the calculator. We're going to go to Desmos to help us figure out where that point is, or where to estimate where it is. Okay, we have 3 of the 4. There's one more. How do we find the horizontal asymptote?
Can you go to the paper? Thanks. We gotta graph it.
I think we have to count the number of x's, right?
Oh, count the x's. It's 3 x's. Well, it's 1 when we cancel them out.
Well, okay. When we count, we're going to bring them back in.
Oh, okay.
Yeah. So pretend like as if the x's are that they're not crossed out. So how many do we have?
Do we count the ones that's in the parentheses and out?
Yeah, yeah. Every
Okay,
x.
4.
Count. Hmm.
4.
Mm-hmm. How do we determine what to do? The previous problem.
The outside.
So before we had to count the number above, count the number below, and then compare them. So how many do we have above on this previous one?
2.
2. How many do we have below?
2.
2. So if the number is the same, then you just have to rely on the coefficients. Just have to look at what's in front, and then that's our number. 1 over 1 is just 1. But if the denominator had more x's, let's say if it was 2 above and 3 below, then it's always going to be y equals 0.
Would you still place
So it's either going to be the fraction in front or it's going to be 0, depending on whether you have matching number of x's or whether the denominator has more x's.
Okay, on the new equation, would you place an x at the denominator too? In front?
No, we won't. So how many do we have above?
How many, what you say?
X's.
4.
How many do we have up top?
2.
2. How many do we have below?
2.
Okay, are they the same?
No.
Well, I have 2 x's. If I have the same number of x's above and below, then my horizontal asymptote is just the fraction of the numbers in front. Let me know where I'm losing you.
On the x that's on the outside.
You're getting thrown off by this x here?
Yeah.
Okay. So how about this? Let me rewrite this problem because that x looks like it's different than these other x's, right? Let me write it this way. Maybe this will be more visually more helpful to you. This x is same thing as this problem. It's just that I know it looks a little different. It looks like it's sitting in front. Let me write it this way. Okay. Does this form help out better?
Yeah.
So that x, if you want, you can always put a parentheses x minus 0 around it to make it match the other pattern. It's the same thing, but maybe it's just visually, it doesn't look as different as the others.
Okay.
So if you want to look at it in this format, how many x's do we have above?
2.
2. How many do we have below?
2.
2. So if I have the same number of x's above and below, then I'm just going to look at the fraction of the numbers in front, and that's my horizontal asymptote.
Okay. So it would always be x minus 0?
Yes, that's right. If you see x by itself, it's always x minus 0. So if you always want to make that adjustment to help you visually, you can do that. Yeah, these are the same things.
Okay.
But maybe this is more easier to visualize. So let's graph what this looks like. Let's graph the boundaries, and then we can go to Desmos. So I have dotted line, boundary. I have a horizontal line, boundary. I have an X intercept at 0, 0. I have a hole at -2, but I don't know exactly where that hole is yet. So I'm going to go to my graph and find out.
You can't plot that one on the -2 on the x-axis?
Yeah, the -2, it's not going to land on the x-axis. It's going to be some weird decimal value.
Oh, okay.
But if you want to plug in, okay. So here's what you can do. If you don't want to rely on the Desmos, you can plug -2 into the x's that did not cancel out. So if I were to
plug it
write
into
this,
one
this
or
would be
both of them?
into both of them.
Okay.
So if I take away the x's and if I re-plug in my -2, I would get -2 over -2 minus 7, -2 over -9. That's 2 over 9. So that's like that's like 0.2 or something. It's like a really small positive number. So if you want, we can do this like somewhere here.
Okay.
Oh, I'm sorry, it's a hole. So we want to put a big gaping circle there. But we have an idea how the graph's going to look, right? It's going to kind of hug along these lines. So we expect the graph to be something like this, and then something like this. They're all going to kind of have the same shape. But we'll go to Desmos to confirm. So I'm going to undo my previous graph. I'll just go to the gear, circle gear, and then hit delete all, and I'll start again. Type in everything in my original problem. Parentheses. Go to my circle gear table, and I already have some of these points identified, so I'll just maybe pick some points around here, around to the like between 6 and 10 maybe, just so I can have some idea where they are. I'm copying them down. Okay. All right, so 1 is at -0.25. All right, so I have an idea how the graph's going to look. Six, 7, 3.5, 8, 2.67. Not being very accurate here, but It's okay. I just need to have some idea where to target my graph. Okay, so to kind of help you along with some of these project problems here, now we're going to be building a function based off of properties. Okay, so this is example 3 here. Can you create a function with one hole and 2 vertical asymptotes one hole, 2 vertical asymptotes, no X intercept, and a horizontal asymptote at y equals 0. Okay, tell me where you want to start or what you need help with.
How do I know this, the whole, like, starting it off? Would I have to rewrite the equation multiple times to find it, or?
You can just create a scenario. You just create a scenario where something cancels out. So what do you want to build?
Tell you the numbers, or?
Mm-hmm.
Okay, x minus 3.
Okay. There you go. You have our hole taken care of.
And then,
so I'm going to just put a X here just to give us some visual reminders that we have the hole built.
X plus 6.
Okay, where do you want to put that?
The denominator.
Okay.
And x, am I able to do x minus 1?
Where?
On the numerator?
On the numerator?
Mm-hmm. Oh, would that have to be in front of x plus 3?
So it says no X intercept.
So that would be it, or?
Well, you have one vertical asymptote.
Mm-hmm.
But it's asking for 2 vertical asymptotes.
But I'm not able to do x.
You can. I mean, X is the same thing as X minus 0. Do you want to do an X minus 0?
Yeah.
I mean, it doesn't matter, right? You can choose any number you want. But the question is, where do you want to put it? It could be X minus 1, it could be X minus 0, but
Oh, wait, on the denominator.
denominator. You want, wait, what do you want to do? It doesn't matter. X what?
X minus 0.
Okay, that works. Any X's here?
No.
Why not?
Because it canceled out.
Okay, because of the hole.
Mm-hmm.
But why can we not put like an X plus 1 or something up here?
because it asks for 2 vertical asymptotes.
Okay, true.
And that would be an X intercept.
Right, and it says no X intercept.
Mm-hmm.
Good. Okay. And it says horizontal asymptote is y equals 0.
How would we find that one?
How would we find that? So do you remember how we did horizontal asymptotes here? We count the number of x's above, we count the number of x's below, and we compare them.
Okay, well, it's 1 x in the numerator. And 3 in the denominator, so 4 x's.
Now, okay, we're not going to add them together. We're just going to compare them.
So would it be 1 over 4?
So
isn't that how it's wrote up there?
Okay. So I see where you're going, and I want to just kind of go back to this scenario here. So this one, you see how there's 2 x's above? And there's 2 x's below? We don't do 2 over 2 as our asymptote. The 2 over 2 is just telling us what to do next.
Okay.
The 2 over 2 tells us that these are equal. So if they're equal, that means the numerator and denominator is growing at the same rate, and we just take the number in front as the fraction. So it's 1 over 1.
Okay.
But if the numerator is less than the denominator, let's say it's 2 over 3, then we don't write 2 over 3, we just say 0, because the denominator is growing faster than the numerator. So if the bottom is higher than the top, then it's always going to be y equals 0.
Okay.
So pretty much it's either going to be y equals 1 or y equals 0. That's pretty much the options that you have. So
would that one be, since the denominator is going faster, would it be y equals 0?
Yeah. So we don't have to do anything. This the horizontal asymptote y equals 0 has already taken care of itself.
Okay.
And then from here, you can go to Desmos, graph it, build your asymptotes, and you have 2 vertical lines and a horizontal line, and then just follow what the graph does and just graph it. Okay, I think you're in better shape now. How do you feel?
Probably a 3.
Okay.
If I was to scale it.
Okay. Because I kind of, because what we're going to do is the problem is going to, if you go back to the project, it'll tell you the properties, and then from the property you'll build your function, and once you have your function built, then identify the parts that you have. So here, whole is at 3, vertical asymptote is at -6, vertical asymptote x equals 0. There's no X intercept. Desmos, graph it, and then that's pretty much problem number 1.
Okay. Do I when I graph it, do I write it down and then?
Yeah. When you graph it, just go to Desmos, graph it, and then put this on a sheet of paper, and then you can just plot the points, and your graph should look like Desmos, but then with just more detail. Yeah, but start with dotted lines though. Your dotted lines will always kind of act as boundaries to help you know how the graph is going to kind of move.
Okay.
But they're all going to kind of be curved like this, and then if you're stuck with the shape, just go to Desmos, and it'll just basically match whatever Desmos tell you. Okay, so I think you can make good progress. And
am I able to rewatch the video?
Yeah. You know what? Yeah, let me stop recording. You can watch the video, but I'll also put this on YouTube, and I'll send you the link there as well if you can't access it in Teams.
Okay.
All right, good. So if you're stuck, hold on a second.